Okay, so good evening to this lecture on machine learning. Uh, and today we will be looking at dimensionality problem and decision trees. We'll spend an hour on dimensionality problem and the remaining time on the decision tree. And also we'll be solving one question like always for the common part of the GATE syllabus. In dimensionality problem, I will talk in detail about principal component analysis because that is relatively much simpler to understand. And linear discriminant analysis, I will motivate the problem. Why do we have another one compared to what we already have? There are two ways of dimensionality reduction. Why do we have linear discriminatory analysis? But we will not be going to the mathematical proof of that because that is a huge proof that is present and that won't be required for the exam. And also, it's very difficult to understand now given the time constraints. So I would suggest you not to go with that. I mean, if you'd have time, then I can teach also if I have time. But seems like I won't be getting time to cover that entire syllabus. If I consider that, that will take one class in itself. So that's why I want to skip that. But we'll see. Okay. But we'll talk about PCA and decision trees today. So that is the topic of discussion. Tomorrow morning at 10 a.m. we will be talking about SVM. And since SVM involves a bit more math, I want to keep one easy topic along with it. So we'll discuss about k-means clustering, which is a relatively very simple topic, k-means and k-midoid clustering algorithms, and that will make things very much simpler. So again, quick glance at the syllabus. We have covered the parts in gray. We will cover the parts given in bold today, and tomorrow we'll be talking about the clustering algorithm and support vector machine. And next week we will talk about feed-forward neural network, and that should be the end of the course. Okay, so now let's start with a question on DSA. So consider a binary max heap that is implemented using the array. Which among the following represents a binary max heap? So here what you can do is, so you just have to remember that for a node n, for a max heap, the value of the node n should be greater than its children, right? Value of the node should be greater than the children. And now given this array form of nodes, it's a complete binary tree. So the first node is your root. Then next value is the left node, left child of that, right child is the next value. Then this is like a top down bottom level order traversal. Okay, so this is the option A actually that I drew here. Okay, and if you see, I think this is a max heap. So A is a max heap. It's saying more than one option can be correct. So let's look at the second option. Second option is 25, 16, 13. See, I can stop here. I can say that 12 is less than 13. So that is a violation of the max heap. So B is not the answer. Let's look at C. 25, 14, 16. So far so good. 13, 10, 8, 12. Yeah, so this is a max heap. See, every node has value greater than its children. So C is correct as well. Finally, let's look at option D. 25, 14, 12, 13, 10, 8, 16. See, the last node is 16. 12's right child is 16, but 12 is smaller than 16, so D is also not the right answer. So I can say that option A and C are the correct answer. Okay, so let's talk about, first we'll talk about dimensionality problem. So what happens is when you try to build a model, okay, when trying to build a model in the training part, which is when you're trying to find out the hypothesis or when you're trying to fit the data uh, to the algorithm, then the training gives some training error. Now it could happen that in scenarios where your training error is high, let's say this is a very simple example, okay, because here your model, the line is not very perfectly fit to the data. So your training error is high. You can say that the model has underfit. One technique to reduce the underfitting and improve the model is to consider more number of features. So let's give an example. Let's take house price problem. So your X denotes the features of the house. Let's say the features is how much square feet the house has, and your Y denotes the price of the house. So just by knowing the square feet, that is not the very, I mean, you can maybe make a model using just the square feet, but if I tell you that, if I also give you an information about, so from here, I also give you an information along with square feet, you also have the number of rooms. Is it a 3-room flat or a 2-room flat or a 1-room flat? Then this information might be better than the previous information. So one way to make the model better is to consider more number of features, and you can increase the number of features in your training set to improve the model performance. But what happens is if you try considering improving the number of features, okay, it might not always work out. It might not always be the case that by increasing the number of features, you will get a better model because some feature could not be very correlated to the data set. It can very much happen, and because of that reason, because of the lesser correlation between the feature you add with the output variable, then that won't be the right way to do it. So, and also there are two issues if you consider a bigger data set in the sense more number of features, right? If your number of training sample is less, which means number of data points, if the number of training samples is less, then the performance of the model may not increase. The performance of the model may not increase, and this problem is called curse of dimensionality. The second problem that can occur is when you are trying to consider more number of features, right? Your complexity of the model will also increase. So the model complexity, because now you have more number of features, so you have to do more number of calculation. That is also a pain. For example, if you let's say take k nearest neighbors and given a point x test and you want to find its nearest neighbor, you were doing a summation across each dimension. Now, if you increase the dimension, then you have to do more number of summations, more number of calculation of the distance metric. So that is another issue here. So sometimes your performance may not increase, which is the curse of dimensionality problem, or it can also happen that the model complexity increases. So formally, so in a formal scenario, consider a d-dimensional feature vector. Okay, in the sense x is nothing but x1, x2, x3 till xb, such that x belongs to a d-dimensional space. Okay. Now assume there are two classes. So the number of classes are two. We are looking at a classification model, and so one I call omega 1 and the other I call omega 2. Two classes are present. And just for simplicity, let's say that the variance of the class 1 and the variance of the class 2 is the same, but their mean may not be the same. Okay. Now, what happens is, if let's say you are trying to build a naive Bayes classifier. So in a naive Bayes classifier, what you try to do is, so in a naive Bayes classifier, which is a generative model, what you do is you try to fit the probability of x given the data um, given the class. So yeah, given the class, what is the data? You try to fit the probability distribution. In the sense, okay, this is actually not straight. Okay, so what I wanted to say was, let's say you have some set of data points, and let's say I denote with the color green the probability distribution of x given omega 1. So let's say that is the probability distribution is something like this. Okay, so this is the probability distribution. So here in the y-axis I have p of x given omega, and in the x-axis I have x, and this is the corresponding mean for the class 1. So this is the for class 1. Let's say that the naive Bayes classifier fits this distribution for class 2. Okay, so it might not look like the same, but let me try. Okay, yeah, okay. So this is for omega 2. Okay, and this also has some mean mu2, which relates to our definition that the mu1 is not the same as the mu2. But what I want to say is the standard deviation, which is a variation across the data set, this thickness of the curve is the same. Okay, it might not look in the diagram, but just assume that the thickness of the curve are the same. It more or less looks the same only, but okay, fine. So typically this graph says if you have any data point which is, let's say here, let's say this is one x test you have, okay, then what your model will say that x test has a probability something which is some non-zero value for p of x given omega 1, but if you see it does not fall into the region of the probability of x given omega 2, so that will be 0, and then you can say that the class belonging to this data point is omega 1. So, but if you notice something, there is a region that is overlapping, right? This region is overlapping, and that is a region of error, because over there your model is confused, because here let's say I put a threshold. Okay, let's say I put a threshold here, and if I say my p of x comma x given omega is greater than threshold t, then I will predict omega 2, and if it is less than t or less than equal to t, then I will predict omega 1. But if you see any region, let's say here, you are predicting omega 1, but it could also happen that it belongs to omega 2, as you can see, right? So that is the issue. And similarly, if in this region, which is the region to the right of the threshold, there is some probability of omega 1 also occurring, but your model is saying that no, it should be omega 2 only. So that is the issue here. So this is called the region of error. So the just a second. Yeah. So the region shaded in blue is called the probability of error or the region of error. Let me call it the probability of error. Okay. Probability of error. Now, one thing that you can actually do is so what we have to do is okay. So okay. Now if I ask you what can you do to solve this problem? So there are two ways. Okay. One way is there some way I can copy this diagram from here to here? Let me check. Copy. The way I can copy this diagram, that would be helpful. Okay, no problem. I will draw it again. That's fine. So one, okay, okay, okay. Let me explain using this diagram only. So one solution that you can do to reduce the dimension is if I somehow move this distribution a bit to the right, which means my mu2 will change, or in other way, the separation that I have between these means, if I can increase that separation, then the overlap will decrease. If you can understand with the, so my standard deviation has not changed. So the class is still not very the same. The width of the curve is the same. But if I can increase the separation between the means, that could be one way by which I can reduce the probability of error, because then the overlap will be much lesser. Okay. Other thing that I can do is something called, if I can reduce the variance of each class. So my class is now not so fat, the curve, it is much more thinner. That can also reduce the probability of error. Again, we will discuss this with an example later on. So this is the two methods that I called is called linear discriminant analysis. But as I said in the beginning of the lecture, I will only motivate you on why we do linear discriminant analysis, but we will dive deep into PCA more than linear discriminant analysis. So let's start with PCA. Okay. Now PCA means if you have a d-dimensional data set, you somehow want to reduce the dimensionality of the data to, let's say, d dash. So d dash denotes the lesser the dimensionality of data has been reduced. So now how does PCA help in doing this is, consider there are n number of d-dimensional feature vectors. So there are n number of data samples, and each sample x is a and d-dimensional feature vector. So my x is a set x1, x2, xn. Each xi belongs to a d-dimensional space. So there are d data points. And so the mean mu is nothing but 1 by n summation k equal to 1 to n xk. So my mu will also be a d-dimensional vector. For each dimension, it will compute the mu. It will compute the mean. So the idea that I want to propose today, that PCA proposes, not me actually, is that let's consider a set of some data points. Okay. Okay. Let's consider this set of n data points. And what I will do is I will try to fit a line. Let's say the line goes from this part. Okay. Let's say this is the line. And this line has a unit vector denoted by E. And you can just denote as a vector. It has a mean that I call M. Okay. And what I do is I project my points on this line. So this line, this projection, I project this line on this, I project this point on this line. I project this point on this line, I project this point on this line, I project this point on this line, this point on this line, this point on this line, this point on this line. So let's assume that this was a two-dimensional data space. This was in two dimensions, x and y, the points. Now, if you are projecting it on a line, then you are trying to reduce the dimension from 2 to 1. Okay, fine. Now, what will be the equation of the line E? With respect to any x. So for any x, every line has a slope plus AE, where E is a unit vector which has a norm of 1, length of 1. And so if I multiply that unit vector by A, that will denote the projection of x, position of point x on the line E. Okay. Which means if I consider any point, let's say here, which is xk, then xk is nothing but m plus ak of E. So this is my E. Ak into E will be this part. Okay. And m denotes the slope from the origin. The slope, okay, I hope you can visualize that. So in essence, the AK denotes the position of xk on the line E. Okay. Now what I want to do here is I would want to minimize the error. So you were trying to project your data in two dimensions. Let's say this was two dimension. Now you are trying to project the data in a single dimension, right? You are trying to project the data in a single dimension. So there will be some error because your previously you had two axes of data points. Now you have a single axis of data points. So you have to pay some cost for that, which is you will have to pay some penalty for that, which is your error. Now the error is nothing but what? Your point was xk. Okay, sorry. Your point was xk, and your line equation is with respect to the line, your point is m plus ak of e. So the error function j will be nothing but sum across all k equal to 1 to n, right? What is the value as per the line, which is m plus ak of e, minus what is the actual point xk square. So this is the sum of squared error between the actual point xk and your projected point, which is the line you found. Let's say the line is e, and m plus ak of e denotes the position of your point xk on the line e. Your value of the line your value of the point with respect to the line e, projection of the point with respect to line e, that minus xk will denote your error. So now my goal is to, as always in machine learning, you will have to minimize the sum of squared error in terms of your a. So the goal is to minimize j with respect to a. This topic might sound a bit boring, but as always, I have to still teach, so please bear with me. But the next topic which we'll learn today, which is decision tree, will be much more interesting. So to minimize this, first let us assume that E is fixed. So you have fixed your unit vector E. So again, bear with me. I will explain this. So my cost function J, which is A1, A2, A3 dot 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 A, which is a function of all the A's and the unit vector E, is nothing but equal to, I will just copy whatever is written on the previous slide, k equal to 1 to n ak of e minus xk minus m the whole square. Okay, so I can now expand the square term and I can say this is nothing but k equal to 1 to n ak square e square minus 2 into summation k equal to 1 to n ak of e xk minus m plus summation of k equal to 1 to n xk minus m the whole square. So now see, I told you that your e is fixed, right? And I want to minimize this function j with respect to ak. Okay, with respect to a or ak, whatever you can say, with respect to ak. Okay. The third term of this equation is not dependent on ak. So I can, if you differentiate it, if you differentiate a constant with respect to x, in this case ak, you'll get 0. Okay. So the third term can be ignored. Also, if I have told you that E is a unit vector, then the norm of E square will be 1, because the length of a unit vector is 1. So then now I can calculate dj by d of ak, which is nothing but 2 into summation k equal to 1 to n ak. So I substituted 1 here, and if you differentiate ak square with respect to ak, you get 2 ak. I hope that is clear. Minus 2 into summation k equal to 1 to n. This ak will just be e xk minus n. Okay? This is just basic differentiation. Okay, and I can equate this to 0. So if you solve for ak, you get ak is nothing but E transpose xk minus n. Now, what does it mean? It means, so geometrically it means, again, let me write this down, it's an important point. Geometrically it means ak is nothing but the orthogonal projection of xk on the line that is passing through M or passing through the mean. Nothing but. So what it means in very basic terminology is, if you are not able to understand, if I take any point, let's say this point, okay, and you want to project it on the line E, because your E is fixed, the distance AK that the max you can get is the orthogonal line, this one. If you make a line like a slanting one, then that will have a the length of it will be more. So the shortest line that you can have here is exceeding the limit. So let me see, exceeding the character limit. So what I'm saying is, they're saying that if your E is fixed and if your point xk, the smallest projection of that xk on the line, which is ak, will be nothing but the orthogonal projection, which is the projection perpendicular to E. Because if you have something like this, which is a slant, okay, which is a hypotenuse of maybe a right angle triangle, then Pythagoras has told that the hypotenuse is a sum of squares of the base and the perpendicular. So the shortest line that you can generate is the orthogonal projection. And the equation for that is this. Okay, so this is okay. Now what we do is, now we will equate the equation, we will now differentiate the equation J with respect to E. So writing it again here, J of E is nothing but summation of k equal to 1 to n ak square minus 2 summation of k equal to 1 to n ak E x transpose minus, oh sorry, writing anything, okay, ak E transpose xk minus m plus summation of k equal to 1 to n the norm of xk minus m square. Again, if I differentiate this with respect to E, the third term is not dependent on E at all, can go to 0. Even the first term is not dependent on E, can go to 0, right? So I am only left with the middle term. So if I differentiate this, okay, if I just write it out like this, let's say, okay, so it will be nothing but minus of summation. Again, I can ignore the constant because that is just to scale. If you ignore it, it won't make any difference. Okay. So minus summation of, okay, one more thing that I will do here is the value of AK that I found in the previous slide, which is E transpose XK minus M. I will substitute it there. Substitute the value of AK here. So I get E transpose XK minus M into XK minus M transpose E. Okay. So this I can also write this as E transpose summation xk minus m transpose E. Okay. Now, this result here is called the scatter matrix, which measures your distance of xk with the mean. Okay, what is the spread of the data? So if you know something called covariance of point xk, that is nothing but covariance is nothing but, so this is related to covariance, popular in statistics, which is nothing but 1 by n summation k xk minus m multiplied by xk minus m transpose. So that this measures the spread of data, how wise your data is spread. And as I said, you would also want to minimize this value, right? So in essence, what happens now is your J of E is nothing but minus E transpose SE. So the scatter matrix, I call it S, where S is summation k equal to 1 to n xk minus m xk minus m transpose. So this way you're trying to reduce the variance of the data set. So that is what you want as well, right? Okay. So this is your objective function. Now, other thing that you also have to know is, so my goal is to minimize J of E, right? Which also means that I want to, so J of E is nothing but minus E transpose SE. So I can also say that to find out if you want to minimize minus of E transpose SE, I can also maximize the negative of it, which is E transpose SE. Instead of minimizing minus E transpose SE, I can maximize E transpose SE, correct? So now this is a maximization problem under a given constraint that the norm of E should be 1. So this is the norm, which is root over E transpose E. Square of it denotes the magnitude, so which is E transpose E, subject to the fact that this is 1. So this is nothing but you can solve it by using a Lagrangian multiplier method. This is very simple, guys. Don't worry about this. Okay, I will explain what is this. Although this is not in your syllabus, but they have PCA in your syllabus, so not sure what they were trying to do here, but still, because without this you won't be able to solve this equation. So Lagrangian multiplier is nothing but your U, which is the final thing you want to calculate, is nothing but whatever is the given function you want to calculate, E transpose SE, maximize, sorry, minus a factor lambda. And what I can do is, I am saying that E transpose E should be 1. I can also write this as E transpose E minus 1 should be 0. So that I can put it here. This is my constraint. Okay, this is the fact. So again, I'm explaining in a very vague manner. I mean, very brief manner. Lagrangian. There's a whole new topic, Lagrangian. But the thing is, what you want to maximize, which is E transpose SE, minus lambda times your constraint, and your constraint equated to 0. So your E transpose E should be 1 because E is a unit vector. So E transpose E minus 1 should be 0. And then E transpose SE minus lambda times the constraint should be minimized. So I can differentiate this with respect to E, du by dE, which I get 2 SE minus 2 lambda E equal to 0. And then I can say SE is nothing but lambda E. Now look at this equation very carefully. Lambda is a constant. S is your scatter matrix. E is your vector. So if you have learned eigenvalues and eigenvectors, see, S is a matrix. Eigenvalue and eigenvector says if you multiply a matrix with a vector, in this case E, S times E, is nothing but same as you take that vector E and multiply it with lambda. So your entire spread of data that you had, which was in your scatter matrix S, can be mapped to the unit vector E subject to lambda multiplied by a eigenvalue lambda. So my E here is my eigenvector and my lambda is the eigenvalue. So if I can calculate the spread of data using S, which is xk minus xk minus m transpose, which is a covariance matrix, and if I can calculate the eigenvalues of S, okay, which is another problem that you might have learned, how to calculate the eigenvalue of a matrix, and also if I can calculate the eigenvectors of it, okay, then what I will do is, see, now I'm trying to, okay, so this you understood that this equation at the end is nothing but the equation that you have to maximize, right? To maximize this equation, you have to consider the lambdas that are maximum. So for instance, if you have a, let's say if I take any matrix A as 1, 2, 3, 4, typically if you try to calculate the eigenvalues of this matrix, you will have two eigenvalues, lambda 1, lambda 2. If I have, let's say, a three-dimensional matrix, then you will have three eigenvalues, lambda 1, lambda 2, lambda 3, correct? So, and each of the lambda eigenvalues, each of these eigenvalues will give you a corresponding eigenvector. What I have to do is, let's take a small example. Let's say my D is, let's say my D is 5, which is the number of columns in my data set is 5. And so my scatter matrix eigenvalues are lambda 1 till lambda 5. And similarly, I will have 5 eigenvectors corresponding to those eigenvalues E1 till E5. Let's say I want to reduce this to dimensionality 2. From 5, I want to reduce to 2. If you want to maximize this function J of E, which is E transpose SE, what you will do is you will consider the top two eigenvalues. So lambda 1 could be some value. So in this scenario, you will consider the top two eigenvalues. So let's call it lambda 1 prime and lambda 2 prime. Lambda 1 is, let's say, the maximum eigenvalue you get. Lambda 2 prime is the maximum second most highest eigenvalue you get. Correspondingly, you will have your E1 prime corresponding to that eigenvalue and your E2 prime corresponding to this eigenvalue. And these two eigenvalues are nothing but called your principal components. So steps are very simple. First, what you have to do is you will be given the data set. Okay. First, you can map those data set as x equal to m plus sum over I equal to 1 to d prime ai ei, okay, which is you calculated the eigenvalues, which is ai, corresponding eigenvector ei, and multiply them, and this will be your final value for x. And the second one is the cost function is nothing but j for d dash number of. Okay, I was talking on mute. So j d dash is nothing but k equal to 1 to n, the norm of m plus I equal to 1 to d prime ai ei minus xk square. A minute, there's some issue with the pen. Minus xk square. So if you given a data set, you will have to calculate the scatter matrix. And if you once you find the scatter matrix, which is nothing but your covariance matrix of the data set, so make sure you learn about how to calculate the covariance. And once you calculate the covariance, you can calculate the eigenvalues of those covariance. So again, if you don't know how to calculate eigenvalues, then please do so. That's also in your GATE CS syllabus as well, engineering maths. Once you calculate the eigenvalues and the corresponding eigenvectors, take the top two eigenvalues, and they might have a question directly that can you find out the can you find out the two principal components for this given data set. Again, they might also give you the scatter matrix because it will be a pain to calculate that much in the given amount of time. So they might give you the scatter matrix and tell you that which are the which are the principal components. So just calculate the eigenvalues of the scatter matrix, and then calculate the top two or top k, whatever they are asking. Top k could be 2, 3, whatever they ask. Corresponding eigenvectors, and then output the answer. So this was PCA in a brief setting. But again, as I said, I won't actually dive deep into something called LDA, which is also there in your syllabus. But I will motivate on why do we need an LDA if you already have a PCA. Why the heck do I also need an LDA? Okay, that should be enough. But I won't actually go to the mathematical proof because that is something that will be very difficult to understand now. Okay, but hope if I get time, then definitely, but not today. So if you see PCA, right, all in all, what PCA was trying to do was PCA just looked at your x's, your xi's, and it tried to project those xi's on a reduced dimensional space. But nowhere PCA considers the yi's, which is your class. Does it belong to class 1 or class 2? And why it should consider is, consider a scenario where your data set is like this. Let's say the data set is, the reds denote your one class and the greens denote the other class. Okay. Let's say that PCA doesn't know this information. It can only see the xi's. It doesn't know which class it belongs to. What PCA does is, PCA, let's say, fits this line. Let's say PCA fits this line. Okay, this is my E. The PCA's E. Okay. Yeah, this is the PCA's E. I argue that I can only argue if the pen works. Yeah. So I argue that this line is a better projection of the points on the plane. Why? See, look at the first line, or let's look at the second line first. If I try to project my points on this line, which is the line number 2, I get something like this. This falls here, this falls here, this falls here, this falls, let's say, here. Okay, this falls here, this falls here, and this falls here. Okay, and when they fall in this line, let's say your probability distribution is, and if you model that using naive Bayes, your probability distribution is something like this, let's say. Now, and for the other class, is this, is this, is this, and this. And so your probability distribution for this one is this. Now see one thing very carefully here. Is there any overlap? No, because the projection of the points on this line caused no overlap, right? But if I consider the other scenario, let's say I consider the scenario, okay, the other scenario where I consider line 1, then you can see the problem. See, line, this is going here, 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 this is going here. So these are the projection of the points on this line. Similarly, these are the projection of the points of the green line. Okay. And now if you try to model this as a probability distribution, see, this is falling like here. So you are trying to, so the green one, let me color in green only. This will be like something like this, something like this. So see, because the probability dips here because there are red points are there here. And similarly for the red part, it could be like this, okay? Something like this, okay? Because see, at this region, your red points are more than the green. So maybe, okay, the green points are more than the red, sorry, for this region. But if you look at this region, the red points are more than the green. So your probability distribution, something like this. So you can see a considerable overlap here, which is something that we not require, if you remember the start of the lecture. But TCA cannot differentiate between 1 and 2. It just says, okay, this is one vector that I found, 1. This is one I can find here. This is absolutely okay. And this is also absolutely okay, E2, E1, E2. But what I can tell you, what you saw just now is E2 is a much better projection compared to E1. And that is where LDA comes into play. What LDA does is, LDA also considers the class information. Let me come back to the distribution I drew earlier. Okay. Oh. Yeah. So this is the line. And if I project the points, then, okay, let me draw in green only. Then this is the projection of the green point. This is a projection of the red points. Okay. So if you see now that there is considered not much overlap. Now, how does LDA try to find this line is, it considers two different scenarios. One, it calls the between class centrality, which means this is it has a mean mu1 and mu2. So one thing it considers is a between class distance, which is it tries to separate the means out as much as possible, which is this has a mu1, this has a mu2. So between classes, between class mu1 and mu2, omega1 and omega2, what is the distance? It tries to maximize those distance, sorry, it tries to maximize the means, the separating means. It tries to maximize the separating means. And the second thing is the within class distance, which means within a class, the distance of the data points from the mean squared, which is the variance, root over is a standard deviation, it tries to minimize the variance within a class. Minimize the variance within a class. So between class distance means maximize the separating means. So if I spread out these two distributions, then the probability of error will be less. And also if I try to minimize the variance within a class, just I try to thin out the curve, then also the probability of error will reduce. So these are the two things that LDA tries to also incorporate along with PCA. So that is why LDA is considered to be a better dimensionality reduction technique than PCA, because PCA is much more older. LDA came very recently only. So this is what I wanted to just talk about LDA. It's a long derivation. Okay, it will take a class in itself, and also we don't have that much time. So I will look into it. If we get some time, then we will look into it, or else maybe you can read that. But that is also, I don't think, very important. You should more of understand what is PCA, how do we derive PCA, why do we derive PCA, and from PCA to LDA, what is the reason behind going into. Okay. Now the interesting part of today's lecture is talking about a very, very, very old algorithm, very, very old um, machine learning algorithm, which is decision trees, and a very simple algorithm. Okay, so let's go into decision trees. Okay, so now let's start with an algorithm that you already studied in some previous class, k nearest neighbors. Okay, so let's take a data set which has the following. It is a two-dimensional data set. And this is a good test of your KNN knowledge actually. So please pay attention. So there are two, so, oh, sorry. Yeah, so this is your x1, this is your x2. Okay. Right. Let's say it's a two-dimensional data set x1, x2, and it consists of some points. Let's say these are the points. So this denotes one. The green class is one class. Okay. And the red class is the other class. Okay. Maybe I'll remove this. Okay. So this is your data set. Maybe add one more here. Okay, fine. Okay. If I ask you a very simple question, if you are using KNN, let's say the test, and let's say the value of K is 3. If you have a point here, X, which class will you classify this point? What KNN will do is, KNN will try to find the distance metric, you can put anything, Manhattan, Euclidean, anything you can do. And what KNN will actually do is, KNN will try to find the distance between all points, right? Distance of X with all the points, look at the top 3 points, and then say that the class that I nominate for the top 3 is the red class and X belongs to the red class. This we have already seen. Nothing changes now. Nothing I have said new till now. But if you visualize the data, let's say I am here. Let's say the next point is here, X. This is another point, X. Okay. Is it redundant or is it necessary to actually check this X with every point in the data set? I can clearly see that this is also a data point that has a label red that belongs to the class red. So what people thought was, what we can do here is we can divide the data set into regions. What are the regions? So let's say that first I consider this point. I draw a line like this, which means, again, let me draw a line the way I'm supposed to. Okay, okay, okay. And what I do is I create a tree, and the line I draw on the axis x1, so I first look at x1. So over here, the value of x1 is greater than some threshold t1. Okay, so it could have two scenarios. If the value of my data point is greater than x1, greater than if the value of the x1 dimension of my data point x is greater than equal to t, I go to the right region, which is I go inside this region. And if it is less than t, then I go to the left region. Okay, okay, fine. Now, after I did this split, what I do is I do another split where, let's say this is the split. Okay. Let's say this is the split ID. Okay. And this falls into x2. So I, let's say, call this as t2. So here x2. So this I'm doing on the left region. So the tree will be on the left subtree. If x, so this is t1, this is t1. So it also has two branches. If it is greater than t2, if it is greater than t2, then I am in this region. So then I fall in this region. Let's call it R1. Let's call this R1. If less, I fall in this region R2. Similarly, over here, let's say I break this data set at this point. Okay. So if it is greater than or equal to T2, then I fall in this region. Let's call it R3. And over here, I fall in this region. Okay. So this is T3, let's say. This was T2. Then I fall in this region, R4, which is this region R4. Okay. So far, so good. Now, what did I do just now? Does it help me do this thing? So what happens now is, let's take a point X. Let's take a point here X. And I'm trying to find the prediction for this point. Now this tree will help me to find which region this point belongs to. So if you see, X1 is less than threshold T1. So it is left to the threshold T1. And it is less than T2. So I belong to region 2. So this point X is in region 2. And now what I will do is, instead of calculating the distance from every other point in the data set, I will only calculate distance of point X with the points that are present in R2, in the region 2. So I will calculate the distance with this point, this point, this point, this point, this point. Okay. And then do the prediction. So this now has improved my algorithm significantly. Before I was trying to calculate my distance with every other data point. Now I only have to calculate the distance from a data point within a region. Okay. And then I do the prediction. But if I ask you one more thing, If you fall in region 2, you are seeing that there are only crosses here, right? There are only reds here. There is no green present in the entire data set here. You can just directly say that if I fall in this region, then the class is red. Similarly, if I fall in R1 or if I fall in R4, the class is red. If I fall in R1, the class is green. There could be scenarios where there's a mixture of the two. In that scenario, let's look at the region R3. It has 6 data points evenly distributed between the green and the red class. Over here, you can use any heuristic. You can predict that it has 0.5 probability of a green and also of a 0.5 probability of a red. So now what happened? Previously, inside each region, you were storing the data points so that you could calculate the nearest distance. Here, you do not even have to do that. You only have to store the label. So if you fall in R2, label is cross. If you fall in R1, label is circle, green. If you fall in R4, label is cross, red cross. If you fall in green, label is circle. So from KNN, we come up to this modified model. This is called decision tree. Now, the biggest question that one might have is, how the heck can I calculate the splits? So I split it here, looking at the data set, I split it here, I split it here. How can you calculate these splits into regions? And that is the actual entire this decision tree is entirely this based upon this only. So one example, so if I tell you one more thing, the bad news is finding a decision tree is NP hard problem. Finding an optimal decision tree is a NP hard problem, but there are heuristics that exist. What are those heuristics? So the people have come up with some terms, which is, let's take a particular node X and I split it into two parts. Okay, with set of data points. If in this region it contains all data points of only one particular class, in the sense if it only contains greens or if it only contains reds, then this node is called a pure node. Why it is pure? Because if you fall in this region, if you fall in this node, then you can surely say which class it belongs to. You don't have a confusion. And if there is a confusion between the two classes, then it is called a impure node. So there exist impurity functions that help you calculate that is a metric to calculate the impurity of a data set. Now there exist two ways to calculate the impurity. One is called the Gini impurity and one is called the KL divergence or entropy, information gain and entropy. So I will explain you Gini impurity, and for the entropy we will look at a live dataset example and then try to find out the decision tree using the entropy and information gain. So Gini impurity means if you have a set of data points from x1 till xn, okay, set of data points x1 till xn. They have their own corresponding y's as well. The probability of a particular class K, P of y equal to K, I abbreviated that as Pk. Okay. The probability of the data points having a particular class K is nothing but Sk by S. So what I mean is, so this is my S. Sk means all data points x comma y belonging to the set S such that y is equal to K. So if I have a data set of 100 elements and let's say two classes yes and no, if there are 60 data points of class yes, then the probability of y equal to yes is nothing but 60 by 100. So this is just in that form. So that is, I hope, simple. And S is nothing but the union across each such Si. So S of yes, S of no, if you take the union, that will give you the set S back. The Gini impurity G of S formula is nothing but for k number of classes, k equal to 1 to capital K, Pk into 1 minus Pk. So now think of it this scenario. Let's say the value of K, capital K, which is a number of classes, is 2. Okay. And you have a split such that over here your P1 is 1 and P2 is 0. Okay. So let's say this is the node I'm trying to calculate, n. So what will be G of n? G of n will be 1 into 1 minus 0, P1 into 1 minus P1 plus P2 into 1 minus P2. So this is nothing but 1. Correct? So if you have a pure node, right? Oh, sorry, I did some mistake. So this should be 1, right? Pk into 1 minus Pk. So P1 into 1 minus P1, 1 minus P1. This is 0. Correct. This is 0. So if you have a pure node, which is a node that does not contain a mixture of classes, then that will give you the least impurity because it's not an impure node, it's a pure node. So your graph of this thing doesn't work always. Okay. So your graph G of P is nothing but something like this. So for k equal to 2, I can say G of P is nothing but 2p into 1 minus p. So if you plot if you substitute, let's say for p1 you say as p. So okay, let me do this. Let me not jump the gun here. Okay, let me do it in the next slide. Okay. So what I mean to say is, if the value of k is 2, okay, then my G of P, G of S, and let's say one of the classes I say is P, so P2 is nothing but 1 minus P, right? If the probability of yes is P, probability of no will be 1 minus P. So I say G of S is nothing but summation of k equal to 1 to 2 P into 1 minus P. And this is nothing but 2P into 1 minus P. And if you calculate, if you plot for different values of P, the value of GP will be something like this. So when the value of P is 0, which is, if let's say the class P1 has no probability, which is 0, and the class P2 has a maximum probability, then your impurity will be 0 because you do not have impure node. And if similarly, if the value of okay, so I was saying that if you calculate the graph for across different P, the GP, if the value of P is 0, then your impurity is 0. If the value of P is 1, then also the impurity is 0 because both of them are pure nodes. And if your value of P is 0.5, that is a sad part, then you are actually in the middle, and then your impurity is the maximum, right? Okay, fine. So this is the Gini impurity, and how to calculate the Gini impurity. I just said G of S is summation of k equal to 1 to k, pk, 1 minus pk. Okay, now, so if you look at this Gini impurity only, right? This Gini impurity, what happened is, if your node is evenly distributed, so if you want to, let's say, calculate the Gini impurity of a node n, and it has 50 samples of P1 and 50 samples of P2 of class 2, okay? So 50 samples of omega 1 and 50 samples of omega 2, then the Gini impurity will be the maximum, because if you are in this node, you actually do not know what is the decision, right? It's very uncertain. It's 50-50 chance. So you do not want to do that. You want to divide that tree a bit more further so that this impurity can reduce. So the worst case scenario could be if I have k number of classes, and the probability of each class q1, q2, q3 dot 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 till qk is actually 1 by. If I have two classes, value of q1 is 1 by 2, value of q2 is 1 by 2. If I have three classes, it is 1 by 3, 1 by 3, 1 by 3, 4, 1 by 4, 1 by 4, 1 by 4. And that is the worst thing that can ever happen. So there is one concept called KL divergence, which measures how different are two distributions. Okay. If you do not understand any of this thing, don't worry. You can watch it again and understand. That's fine. But I will also teach you how to solve the question as well. In that, you won't require that much of knowledge here. So KL divergence would mean how different are two distributions. Okay. So the KL divergence of distributions P and Q is given by summation k equal to 1 to k pk log pk by qk. Okay. And let's say I want to find the right distribution P, I can use this KL divergence in the sense I would want to compare P with 1 by k. So Q is nothing but the worst case scenario, 1 by k. And if I substitute the value of qk here, k equal to 1 to capital K, pk log of pk by 1 by k. Pk by 1 by k. I just substitute the value of qk in the equation. Now, why do I do this? Just hold on, I will explain. So now writing it here from here. Okay. I think so. Writing it here, what I can say this is nothing but summation k equal to 1 to k pk log pk. Okay. Pk log pk minus summation k equal to 1 to k log 1 by k. Now, how did this come up? Okay, so this is nothing but I considered pk. So pk log pk. Okay, let me not jump the gun. Okay, let me go it step by step so that you understand. So pk log pk. So that I hope is clear. Then I can write this as pk log pk. So okay, let me write this way. So log of a by b is nothing but log a minus log b, log of 1 by k, right? And log of 1 by k is nothing but log k. So, sorry. So log x is nothing but minus log of 1 by x, right? I hope you know this. So minus log of 1 by k is nothing but plus log of k. So I can write this as summation k equal to 1 to capital K, pk log pk plus summation k equal to 1 to k, pk log k. Okay, so pk log k. Okay, and yeah, okay, fine. Now log k is a constant. I can pull it out, and some. So I have to write in the next slide. So what I mean is log k is a constant. I can pull it out. K equal to 1 to capital K, pk plus summation k equal to 1 to k, pk log pk. And now the summation of k equal to 1 to capital K, pk is nothing but 1, right? If you have two classes, probability p1 and p2, they add up to 1. That's the entire fund of probability. So I can write this as, therefore, I can write this as the, it is nothing but summation of k equal to 1 to capital K, pk log pk plus log k. So this equation, I claim I have to maximize. Why? I have to maximize and find the value of P or Pk that maximizes this equation. And why so? See. Again, log k is a constant, I can ignore. KL divergence compares the how are two distributions different to each other. Okay. If I want to compare a distribution that I want to find, which is P, and how different it is from a distribution Q, and if it is different from a distribution Q, which is 1 by K, I would want the difference to be maximum, because 1 by K is the sad part, is the sad thing to have in a split. You wouldn't want a even split across different classes. So what I'm saying is, I'm writing in red so you remember, this is something that we don't want. And my distribution P, if I want to compare with 1 by K, should be as maximum as possible. Okay, so that's why I'm taking the max. What is the max value of pk for which summation of k equal to 1 to capital K, pk log pk is maximum? Which essence, I can also convert this into something called a minimization problem by doing a minus. So minimization pk minus summation k equal to 1 to k, pk log pk. And this term here, you didn't understand till now, is called the h of s, h of p in this case, which is called the entropy, which measures the uncertainty of the data set. So in essence, my problem is to now calculate for minimum of p, h of p, which is I want to minimize the uncertainty or minimize the entropy. Now, forget the math that I have taught till now. I mean, if you want, what we will do is we will actually do a small example using a data set. I think I put the data set somewhere. Yeah, okay, fine. I think here it is. Yeah. So this is the data set that I have for you. Okay, just a minute. I have to connect my charger or else the laptop will die. Tablet will die, sorry. Yeah. Okay. So look at this data set, right? Look at this data set, and I want to find out the decision tree for which this data set works the best. Okay. Now, this data set has two classes, P1 and P2, correct? So, as I said, finding an optimal decision tree is an NP hard problem, but you can use this impurity functions to calculate the right set of decision tree given the class. In this case, I will use the entropy. Okay. So I have the root of the tree, which contains the entire data set S. And I want to calculate the entropy of S. Entropy of S is nothing but minus summation A equal to 1 to 2 pk log pk. So what is P1? P1 is nothing but, let's say, the probability that the class is yes. And out of 10 data points, 10 data points, 3, 4, 5 are yes. So P1 is 5 by 10 and P2 is 1, 2, 3, 4, 5, 5 by 10 again. So P1, P2 are both half. And if I plug in this formula here, I get minus of 1 by 2 log 1 by 2 plus 1 by 2 log 1 by 2, which is log 1 by 2, log 1 minus log 2, and I always take base 2 here. This is nothing but 1. So see, the entropy is maximum here because your class is evenly distributed, correct? So once you calculate for this parent node, you would consider each child nodes. Okay. In a sense, let's take the weather. So if I consider the weather, it is divided into 3 fields. One is it sunny? Is it cloudy? Is it rainy? Okay. And if I want to calculate the entropy of this data set S given the weather, I will have to calculate the entropy of H of S given it is sunny plus entropy of H of S given it is cloudy. Okay. Let me actually do this. Okay. So let's calculate the entropy of each of these sets. H of S given it is sunny, H of S given it is cloudy, H of S given it is rainy. So H of S given it is sunny is nothing but again minus pk log pk But here I won't consider any other data set except where the weather is sunny. Because I'm telling you that the weather is sunny, so it cannot happen that the weather is cloudy or rainy. So if you only filter out the sunny data sets, one, two, three are there, and out of the three, two are no and one is yes. So minus 2 by 3 log 2 by 3 plus 1 by 3 log 1 by 3. This is for sunny. There will be a similar one for cloudy. There will be something similar for rainy. Okay. And then the final entropy is nothing but the weighted average of these entropies, which means out of the initial data set which had 10 points, you see there are 3 sunny points. So 3 by 10 h of sunny plus cloudy is 2 by 10 h of s given cloudy plus 5 by 10 h of s given rainy. So this is your entropy of s given the weather, okay, which is a weighted average across the 3 different classes it has, sunny or cloudy or rainy. What I calculate now is something called the information gain. So information gain is nothing but whatever was the parent entropy minus whatever is the entropy of the child. So let's say the entropy is S given weather. Okay, let's say the value of this is 0.37. I'm not actually calculating the values, but let's say the values, or let me do one thing. Let me pull up this data set from the internet and then we will just calculate. I won't do the calculation, but we can just actually see the values that are present. Just a minute. Yeah, okay, fine. Yeah, so just a minute. Okay, just a minute. Okay, seems I'm not able to find it, but fine. So let's say you get the value 0.37, which means if I consider the parent entropy, which is 1, the uncertainty is 1, and if I consider the new entropy, which is weather, which is given as given the weather, then I get a information gain of 0.37. Okay. Similarly, I can calculate the entropy of h of s given the temperature, h of s given the wind. Okay, and similarly I can calculate the information gain corresponding to all the 3 entropies. Okay, so maybe today there's lack of time also. I don't want to rush into this thing. I'll just explain the algorithm. Tomorrow we will actually solve an example. So what I want to say is you calculate the entropy of a set S given the split that you want to do. In this case you calculated it for weather, now you calculate it for temperature, and now you will calculate for humidity also. There will be an entropy. And let's say for h of s given weather, it is 0.37, which means if you consider the feature weather as the split decision now, then you will gain an information of 0.37. Your uncertainty will reduce by 0.37. Similarly, there will be some value for this one, some value for this one, some value for this one. So which split will actually reduce your uncertainty the most, which means which split will actually give you the maximum information gain, is the one that you will select as your next feature. So in essence, if you calculate this one, again, I am not calculating, you'll get something like this, which means this is the decision tree output that we'll get, which means initially your data set was containing the first feature is weather. If it is sunny, if it is cloudy, then the model just directly says that it is yes, it's a pure node. If it is cloudy, then it's always yes. If it is sunny, then it again splits on the feature humidity. And then if it is high, then it will say no. If it is normal, then it will say yes. And similarly, if it is rainy, it will split on the feature wind. If it is strong, it will say no and it's yes. So how to actually calculate the splits, we will look into it tomorrow by looking at one of these examples. My plan was to actually cover the entire derivation of this example, but there's no time left. We have 15 minutes, but I don't want to rush this thing. Maybe what I will do is tomorrow we'll actually solve the entire decision tree, but the algorithm is simple. You calculate the entropy of the parent. You calculate the entropy of the parent given any feature. You calculate the information gain of that given entropy, whatever you had, which is the entropy of the parent minus the entropy of the given feature. Whichever will give you the maximum information gain, you will consider that as your split. Once you're split, your data set will be split into subtrees. With that new split, again, you will apply the recursive algorithm to calculate the next split. So again, if you don't understand this, stay tuned. Tomorrow we'll actually go with an example. We'll try to solve one example from scratch. Okay, saying I've raised my hands. No, I have not. Okay, so we'll solve this example and then that will give you more clarity. But more of, I hope you understand what the basics of the decision tree. Okay, and how do we calculate the decision tree and how you are motivated by using decision tree as compared to uh, how do you come from decision tree to from k nearest neighbor to the decision tree. Okay, uh, with this I want to end today's class. Tomorrow we will do is we will first solve an example of decision tree, half an hour this example will solve, and then half an hour I will discuss, or 1 hour we will discuss on SVM, support vector machines. Again, it's something that is a bit more difficult, but not that much. If you understand perceptron, then support vector machine is not a big deal. Um, and then once we have done that, we will go into talking about k-means clustering, which is a very simple algorithm. I don't want to do feed forward because SVM is already a bit complex, and I don't want to do two complex algorithms in a day. I will do one complex, which is support vector machine, and one very simple, which is k-means clustering. Next week, we will be looking into feed forward neural network and other small topics, this linkage and all that. And I think that should be the end of the syllabus on machine learning. Again, crash course only. It's not very detailed one because of the time, but this will actually make you better than zero. So I hope that that is the case. Okay, I'll stop the recording. And if you don't have any question, I can exit the call.